I'm Matt Ahrens. I work for Delphix, and my work on RaidZ expansion was sponsored by the FreeBSD Foundation.
I'm Don Brady. I'm with Clara, and also being sponsored by IX Systems for the RaidZ expansion.
Cool. All right. So has anyone had this problem or know someone who has this problem? You have a full pool. It's all used. You're using RaidZ. What do you do? Well, what you would like to do, your proposed solution, is to add another disk and expand the pool's capacity. But until now, you haven't been able to do that because you have to add entire RaidZ groups at a time. So if you're like a big enterprise customer, you can roll in a new, $100,000 shelf, plug it in with 50 new drives, and you're all set. But if you're a home user, you would just want to go to the store and buy another like $200 drive and put it in there, which you can't do now. But our solution lets you do this. So now you can run zpool attach just one new drive to your RaidZ. It needs to copy all the data around to use the space in the new drive. And then when that's done, you have additional space available. So when it completes, then you'll have the new drive, which in this case is number 6 in your RaidZ group. It tells you about the expansion. Yeah, it took a long time to do it, but it's done now. And now you have more space available. In this case, 600 megabits available. Reminder that the space available is not the same as the space free according to zpool list. So the difference here is zpool list is telling you about how much actual bytes are allocated and free on the disks, versus ZFS list is telling you kind of how much space is available to you if you were to write it, ignoring compression, but taking into account parity, for example. So the key thing here is that the ZFS list is like pretending that you don't have to pay for the parity. We've already kind of taken that into account, versus zpool list. It includes the space, like the free space includes space that is going to be used by parity. All right, so I guess that could be the end of the talk. Like, it works, yay! But that would be a very short talk, so I thought I'd tell you guys a little bit about how it works under the covers. And maybe along the way, you might come to understand why it took 6 years for me to do this. Most of it's because I wasn't working on it the whole time. But what we want to think about is what does the state of the disks look like? So it's useful as a point of comparison to think about what does it look like for a traditional RAID, right? This might, if you don't know the internals of RaidZ, you might be thinking this is how it works. This is how it works with like traditional RAID 4, 5, 6, etc. You have, in this example, 4 disks. The last disk has all the parity. It's the parity of the other 3. RAID 5, it just kind of puts it diagonally across, but conceptually it's the same. So if you were to add another disk, what we need to do is just recalculate all the parity and reflow the data. So we reflow it sort of like a word processor. You make your margin smaller, and now the words flow to the previous lines, just like this. So in this case, like in this sector 4 got moved to the previous row, the first row there, and then we have to recalculate the parity because now we need the parity of sectors 1, 2, 3, 4, versus before we just had the parity of sectors 1, 2, 3. Relatively straightforward. Obviously, you have to recalculate the parity, which has some cost, but you have to read all the old data and rate it all again to different locations. And we have to do the same thing with RaidZ. Like, we have to move all the data around, but the way that we handle the parity is very different because the way that RaidZ handles the parity is very different. So with RaidZ, as I alluded to before, the parity is included in the allocation. So kind of more layers of ZFS know about that parity. And so what we're doing with RaidZ is we're moving all of the sectors, including the data and the parity. So the parity doesn't get recalculated, it gets moved to a new location. So in this case, like sector 5 is the parity of 6, 7, and 8. and we're moving it to a new location on the new disk, but we still have sector 5 being the parity of 6, 7, and 8. So the cool thing about RaidZ is that with RaidZ, from the allocation point of view, the parity might be like in lots of different places. It's not just all on one disk, or kind of by math, we know that it's on, this disk and then that disk and that disk and that disk. It could be in all different places depending on the sizes of the blocks after compression, the sizes of the blocks as they're written. So like in this example, we have 5 and 6 are one logical block, and then 7, 8, 9, 10 are one logical block. So it's kind of a degenerate case where block 5 or sector 5 is the parity of just 6. It's not a full row of parity, it's just a partial row of parity. But the good thing for reflow, for RaidZ expansion, is that when we reflow it, we don't care where the parity is. We're just moving it around as though it were any other sector. And we don't need to copy the allocated space, right? ZFS knows what space is allocated in freed, so we don't need to copy any space that is not actually allocated. Obviously, the typical use case, practically all the space is allocated, so this isn't like a big performance win. There are probably some other use cases that you might run into where like you accidentally configured it with 4 disks, you used it just a little bit, you meant to add this 5th disk that was there all along. You can use expansion for that, and it's going to be much, much faster. So the cool thing is, like, it works. You just read all the data sequentially, write it all sequentially. And because each logical stripe is independent, we don't need to care about where the parity is. And the key thing is that the segments are still on different disks. So the redundancy is preserved. I'll show you kind of how an example of this. So for example, if we think about the blocks 7, 8, 9, 10, you notice those are all part of one parity, like one group. 7 is the parity of 8, 9, 10. And they're all on different disks. And that means that if any one of those disks dies, then we still have 3 of the other pieces of that group, 7, 8, 9, 10. And after moving it, that group 7, 8, 9, 10 is also on 4 different disks. So if any of those disks dies, we still have 3 of the pieces of it. And so we can reconstruct it. Additional cool thing about RaidZ expansion, once you've expanded it, you have all the free space, you have a bunch of free space at the bottom here. That's going to be, however much space was in the new disk is now free space. It's all kind of at the bottom. But in the space in the bottom, or free space that happens to be in the middle, in this example, we can allocate the larger stripe width. So for example, in the block like 7, 8, 9, 10, you have 1 piece of parity and 3 pieces of data. So the ratio between data and parity is 3 to 1. But when we write new data, now we have 5 disks. So we can write 1 sector of parity into 11, and then 5 sectors of data, 12, 13, 14, 15, 16. So you have a better ratio of 5 pieces of data to 1 piece of parity. So basically your space efficiency is going to be better. But this brings up kind of a little bit of trickiness. So like that's great that we did this allocation and it's a bigger allocation, but when we go to read the data, how do we know whether it was written with this old layout with 1 parity to 3 data, or the new with 1 parity to 4 pieces of data? The way that we do this is when we're reading, we need to know what was the logical stripe width. So the way that we do it is we say, okay, while we're in the middle of the expansion, we're still allocating, while you're in the middle of the expansion, you can still use the pool, right? You can still do reads and writes, everything's online, just as you would expect with CFS. And we're still doing writes using the old width. But once the expansion completes, then we'll switch over to using the new width. So all writes, all allocations after that point are using the new width, And so we can use that kind of time point, that TXG, as the cutover time. So any blocks that were allocated before that cutover time are using the old 4 wide, and any blocks that are allocated with the new after that time cutoff time are using the new 5 wide allocations. One kind of little wrinkle about this is that in, like I mentioned before, ZFS list, it tells you how much space you, like how much logical space you could write. It's trying to tell you, it's making some assumptions about how much parity is going to be used in the future, and then predicting like, you're going to be able to write this much data, and don't worry, we have the space for the parities outside of that number. But when we change the data to parity ratio, we can't actually change the way that like accounting works. So you're going to end up seeing like a little bit less. It's going to say you only have 1 terabyte of available space, but actually you can write a little bit more than that because of the improved data to parity ratio. So we talked a bunch about like the end state that this is going to be in, like what does it look like at the end? We've reflowed all the data. But how do we get from the beginning to the end? Like obviously we cannot read in everything from disk, keep it in memory, and then pop it all out in the new layout. Right, so this is an example. On the left, we have the initial state. On the right is the new end state. And each color here represents like one parity group, where like all the sectors of that color are like, one of them is the parity and the rest of them are the data. All right, so we're starting off here. Here's some possible intermediary state, right? Like we've reflowed some of the stuff, but not all the stuff. And these green sectors at the bottom, 29, 30, 31, 32, part of them have been moved and part of them, some of them have been moved and some of them have not. So what happens if one of the disks were to fail? Like if this 4th disk fails, then we'll have lost both sector 29 and 32. So that's a kind of a problem for us, because if this was RaidZ 1, we can only lose 1 disk, which means we can only lose 1 piece of the data plus parity in that group. But in this case, we've lost 2 of them, right? 29 and 32. So we can't recalculate both of them from just a single parity. All right. That would be problematic. And we really need this to work, right? Like during the expansion, this is not like don't just make sure nothing fails while this is in progress. No, that is not how ZFS works. It's all online. All the guarantees of RaidZ still exist, so you can still lose, P disks, where P is the number of parity. If you have RaidZ 3, you can lose 3 disks while you're in the middle of the expansion, and without losing any data, everything is still preserved. So how do we do that, given the problem I just mentioned? So the trick is that the data is in 2 places at once. So the sectors 29, 30, 31, 32, if we've moved some but not all of those, then we make sure that we can still continue to read them from the old locations. So I'm going to move, hopefully the audio still keeps working, but we can, even though we moved this already, we can read it from the old location here, where only one of the pieces of data has been lost. And so we can do the reconstruction. Now, the trick is just, we have to make sure that that invariant is always true, that the data is still at the old locations and we haven't overwritten it. So to make sure that's true, there's 2 key things. One is we have to have not overwritten it yet. The other is, what exactly do we have to have not overwritten? Because I'm showing you these examples where there's only like 4 pieces of related data. There's the data 1, data 2, data 3, and parity. The parity is the parity of the other 3. But you can have like very large blocks, right? Like you can have a 16 megabyte block in ZFS. So does that mean that like the whole 16 megabytes can't be overwritten while I'm in the middle of this? Well, no, thankfully, each stripe is processed independently. So even if you have a large block that's composed of many sectors and many stripes, so like you have a 16 megabyte block, you divide it into 4 kilobyte sectors, that's, I don't know, like a whole bunch, more than 4. But each like one sector wide piece of it can be considered independently. So even with the 16 megabyte block, the first 12 kilobytes of it still works as though the rest of the block wasn't there. So we can reconstruct that first 12 from the first 3 sectors plus the sector of parity without regard to what's in the rest of the block. So that means that we only have to keep a separation of one like width. So in this case, like 4 sectors, not the maximum block size of 16 megabytes. So that's great. But what about at the very beginning? So at the very beginning, I think I have an example of this, maybe not. At the very beginning, you have a problem where, well, the separation is only 1 because I added 1 disk and I have 1 free sector there, and I can only move 1 sector at a time. So I might end up having to overwrite within that same, even though it's only 4 sectors that I have to keep intact at a time, one of them still might be overwritten. So we have a special case that happens just at the very beginning of the expansion where we read a bunch of data, we put it into this reserved space that happens to have been reserved 20 years ago. We thought that we were going to use the first 4 megabytes of every disk as like a part of a bootloader region. And it turns out that like that was probably for some like ancient Spark bootloader that doesn't even exist anymore, was for some old format, you know, it was this is invented like pre-GPT partitions. So probably had something to do with like some old Sun partitions. Thankfully, nobody ever used that space. So this whole time, nobody asterisk ever used that space. We were able to use it here. So basically we can copy the first 3.5 megabytes of each disk into this reserved region that's on each disk. And now the data is in 2 locations, this reserved region and the original location. And then we can overwrite the first beginning of the real locations with all the newly formatted reflow data. So this is showing kind of what happens there. We read the first, it has to be at least kind of the width squared. So in this case, like 5 times 5, it has to be at least 25 sectors total. But in practice, we have this much larger space, 3.5 megabytes. So we read the first 3.5 megabytes, and then we write it to this scratch space, and then we can overwrite the first 3.5 megabytes of each disk, and then atomically switch forward and say, okay, that's all done. Now we can move forward having sufficient separation between where we're reading and where we're writing, that we always have at least 1 stripe worth, and we're not overwriting ourselves. So once we've done that, here we have enough we have at least 1 row of basically unused space, sectors 21, 22, 23, 24, and we can start copying stuff. So we can move the first one. So we read sector 26, we write it to its new location, which is overwriting 21. Then 27 can move to its new location, 28, and so on. Cool. So some of the design implications of this. So it works with all kinds of RaidZs, right? RaidZ 1, 2, 3. Each expansion happens kind of one at a time. So you really are adding 1 disk at a time, doing this whole reflow, and then that's done. But then you can add another one. So if you need to add a whole bunch of disks, well, maybe you should have been adding them as a new group. But if you didn't want to do that, or if maybe it's 1 this month and another one next year, you can do that. As I mentioned, the old data has the old data to parity ratio. The new data has a better data to parity ratio. And during the expansion, disks can fail. But if a disk fails, we're going to pause the expansion and wait for the pool to become healthy again. The problem is that if we were to continue the expansion, then we would both not be able to read from that dead disk, and we also wouldn't be able to write to it, which could result in like two blocks in the same stripe being lost. So we wait for the reconstruction to complete, and then the expansion will automatically continue. All right, fun demo times. Okay, good. Make sure this comes up because the computer is a little slow. Maybe it's a lot slow. Do you want to talk about your work?
Okay, hopefully this is pulling it down from the.
Yeah. Let's give it some time.
All right, yeah, so this is the first time Matt has given this talk, I think 4 times. And this is the first time that actually we're gonna have a demo. And so here's the demo, actually working. I'm using 4 RaidZ 1 and then adding to it. You can see there's 4 disks. And then catch up to the. Okay, so yeah, so Matt mentioned that the space will come at the end. So this will be a good test of people's memory. We'll remember what this number is, 465. I will forget within a few minutes. 465 is how many metaslots we have right now. And so we're going to go and find the disk. In this case, it's SDF. And this is just showing you sort of the awkwardness of administrating a ZPL create, because you don't want to use the SD names. You want to use a persistent name. So this is just finding the persistent name. There's my disk. So then here we go, the main attraction here, ZPL attach. And then as a way of background, this system is like only 4 cores, 32 gigs, and these are pretty slow, like 2016-ish drives. So this is not necessarily the worst case because it has 4K sectors. 512K would be the worst case, but there we go. And then the estimate, a little shocking there, 1 day and 23 hours, 2 days. It doesn't take that long, but let's see. And then we'll go use this that scratch space. And so in the Uber block, we keep track of whether we're using it, where we are in the whole process, and then the offset. The offset is used to tell us where we last successfully sank out the disk. And so here we go. We should be seeing a little bit better, but 24, 25-ish megabytes per second is what this RAID is, this array is capable of. And then for fun, you can see that bottom row, he's only taking writes. That's the new disk. And then you should see at some point, I yanked the disk out just for fun. There it is. All of a sudden that disk is taking no reads because he's not in the array. And then the expansion process will figure that out. And I think there's a status in here. So yeah, I'll do the ZPL status pause until you get that thing healthy again. And so we'll get it healthy again. And basically I just replaced it. I put the disk back in and it resilvered. And once the resilver finishes, then 15 hours later, it comes back and we have our new pull with, let's see, I'll show the status. So it took exactly 15 hours, right, rounded up a little bit there. And you can see that now we have 9 terabytes available for allocations. And see, and then what was the number? Anybody remember that number? 465. Good memories. You'll see here that we got 582. So basically, it's appending that new space onto the bottom of your VDEF. Okay.
Uh-oh. Playing it again. Oh. I tested doing the video, the recording, but not going to the next slide after that. So, sorry.
Okay. I'm going to talk next about how we tested this. This is one of those big features. We want to make sure that we have adequate testing. And so first, I wanted to do a shout out to VStack. They actually stepped up and did a lot of testing for us and provided hardware for their testing efforts. That was nice to have that resource available. So for the test suite, we want to make sure we cover all these cases, yanking a drive right in the middle of the expansion, all the things that could possibly go wrong. So we have several tests that will do that. It'll run the test, and we added a new tunable so that we can actually pause it in the middle. So because with the test, you're running with small pools, and so the time to reflow is not going to be that long. So you want to make sure you catch it. So we have the ability to stop it right in the middle of doing its stuff, and then we can take a disk out, offline a disk, resilver it, do a scrub, do different things in the middle of those. And so those are, I think, important to cover all the sort of the edge cases that could show up in this feature. And then of course negative tests. When you're in the middle of an expansion, you don't want to be able to start another one. So the negative test, make sure that we're not doing those things at the same time. Like you can't do a checkpoint while you're in the middle of an expansion, for example. And then we also added a test. Matt had mentioned that space is not used, although with the caveat, FreeBSD with FAT and MBR partitions, there wasn't enough space to put the loaders in there, so they used that space. But fortunately, we can detect that. So if that's in use, then you'll actually, when you do the attach, it'll say, I'm sorry, that space is being used. And so you have to go rectify that. So in addition to the test suite, we added for Z-test. Are people familiar with Z-test? Z-test is, we run it in user space, ZFS, and we just basically do everything at once, kind of all kinds of different things, adding disks, removing disks. And so in that context, we added, you can specify the kind as RaidZ, and what it'll do is it'll throw into that big mix of all those things an expansion. And so you'll get expansion, and someone else will be doing trim or all kinds of stuff coming and going. So that's a good use. And then we also did a specific mode where we'll purposely go through the expansion, and at some point, I think it's 25, 50, and 75, and roughly, we'll just kill that process. And so it'll come back up and scrub the pool, make sure that it survived a crash right in the middle of the reflow. So that's another good mode. And then to get sort of coverage across all the different parities and sizes of disk, we run it with a script called zloop, which will run Z-test continuously with just throwing a new configuration. Hey, let's try D-RAID, and run a D-RAID run, and we'll do mirrors, RaidZ. And so I added to that mix an expansion, so we can do various runs against all the different configurations, make sure we didn't miss anything. And then finally, we did manual testing, basically, VStack myself in that with real hardware. And then as far as performance goes, I was hoping to have numbers here, but ironically, when I was doing the second run, one of the disks died. I mean, it actually died, and I didn't have another spare, so I wasn't able to continue the performance run. So I'm gonna do that on the side once I figure out what's going on with my disk, and publish those as part of the PR. So that people can see it. But it's the same. Well, actually, you have a slide. No, okay. I'll finish up the testing thing. So for the zloop, you can see this is a real run where basically it'll just throw out, like in the first one out of the gate was RaidZ expansion, and it tried it for in this case 11 disks with triple parity and A shift 9, and then in another run, I think there's one on there. Yeah, it's going to use 4K. So you get the mix running. You just run zloop, and I've run this for hours on end, and occasionally you'll see a bug, go chase it down. Same thing for the functional test. I don't know if anybody ever looks at this output, but if you're doing a PR, eventually you'll get a Z test failure or a test suite failure. You go look at it and it'll tell you like, which test failed. Go look at the logs. Okay, for performance, I don't know if you wanted to speak to this, but basically the takeaway for me, like in running this, is that the read is slightly slower if you're reading the old original data, because we have to bring it into memory and copy out the sections. So there's a little penalty there. And writes obviously improve. So did you want to speak to this at all, or
No.
okay? So like I said, I'll have some numbers, some more newer numbers with 4K sectors. I think this was 512.
Yeah.
And then finally, this is our hopefully final report, the final talk on this. The PR is out for review. We've had some great review feedback, and we're waiting just for a little bit more, which I'm hoping will wrap up possibly tomorrow during the hackathon. And for future, the speed of the reflow, we could improve. There's some things we can do to improve that. Obviously, maybe doing multiple drives at once. If you want to add 2 drives, you don't want to have to wait 12 hours and then wait another 12 hours. Maybe mix that together. But these are all like future things we could do. And DRaid and auto scrub and rewriting existing blocks with new. I've already seen in the discussion board, people are already coming up with scripts to do that. But basically, you just have to copy the data or overwrite the data to get it to use the new parity ratio. Pretty much it. Cool. Q&A.
Yeah, and I'll just mention the right side of the screen here. We get a lot of Qs, so some proactive As. This does a lot of cool stuff that people are like, oh my gosh, wow, it's amazing. It must also do whatever. You could easily since you can do this, clearly you can easily remove disks from my RaidZ. Nope, that is totally different and perhaps impossible. So yeah, we're not defragmenting anything. It doesn't require the mythical BP rewrite project, so you don't get any of the like other mythical benefits from that. But the stuff on the left here, future work, those are all things like DRaid expansion that would fall very naturally into this design, but we just didn't do it in this project. It's already taken 6 years. And like for at least 4 different companies, kind of taking the lead on this. So it really has been a really big collaboration among the industry, and we're very thankful for all these companies sponsoring the work, and hopefully it'll be coming to you soon. I'm hoping that the emoji here, it could be interpreted either as like, we're praying, please let this be the final report, or it could be interpreted as high-fiving, because it is the final report, because we're going to get all the people into the room tomorrow to get it reviewed and get it integrated, hopefully. And then we'll really be able to do the high fives. Okay, yes, Q&A now. Wait for the mic so that they can hear you, thanks.
So just how far can you expand? Like expand once with one disk and then again and again and again, and is there a limit?
Yep.
255?
Yeah, I think the limit is the same as the overall RaidZ limit. So I think even without this, you cannot create a RaidZ that's more than 255 wide. And that is still the case. Can you pass it back there? Thanks.
Multiple VDAVs at once?
So like if you have 2 RaidZ VDEVs and you want to add one here and one there, the design, like the fundamental design would allow that. It's pretty straightforward, but for ease of implementation and also like ease of administration and kind of observability, it's a lot easier to like for observability, from an observability point of view, to just be like, here is the one expansion that's going on, versus having to be able to tell you about each top level of VDEV. Oh, this one is 1% done and that one is 17% done. Even though like, yeah, in theory, like those are independent resources. you could do it and it wouldn't really hurt performance, but consider that on the future work if somebody wants it badly enough. Other questions? Go ahead.
Is it authentic from a performance perspective, such that if one has an imbalance V at it, oops, they have an extra disk here, they can correct the others, will it be indistinguishable in the performance, as if it was always set up correctly?
With the exception of reading the old data, as shown here. So like reading the data, the stuff that was written before the expansion, it's going to continue to be in the old layout. And also because we've kind of, if we go way back, like we've made everything go diagonal. There's an earlier one that probably makes it much more clear. My first one. Yeah, so like if this was all one logical block, then this is kind of what the layout would look like, where the parity actually ends up on all the same disk. And so when you go to read this one logical block, you only have to read from disks 2, 3, and 4. You don't actually have to read from disk 1. After the expansion, the parity is now kind of diagonally across. You see like it's on the last disk, 5 is on the last disk, 9 is on the 4th disk, 13 is on the 3rd disk. And so when you read it in, we actually have to read from all of the disks and then like, tease apart. We don't need the parity, but we need to glue things back together in the right way, the B copy that he was talking about. So yeah, there's like this little performance hit of reading those old blocks. But I think to your specific question about like, created it with 4 and then I want to add 5, that wouldn't really apply because you don't have any space. If you catch it soon enough, then you wouldn't have any space in the old format. And even so, like that performance hit is like pretty minor. I think in this example, it's 2,600 versus 2,300 megabytes per second. So that's like 20%, 15%. Yeah.
So,
Yeah.
Is there any impact on fragmentation when you start to replace the old data?
No.
Changing the layout?
There's no real impact on fragmentation. I mean, obviously, when we do the reflow, it's just like preserving whatever fragmentation is there, and all the free space is in one giant chunk at the end. So that's nice. When you free stuff that's in the old size, and then you're allocating stuff in the new size, I mean, it might, if your data is extremely regular block sizes. So like, if you're doing the one, the case where it might matter is where you're like, okay, I have 4K sectors and all of my data is only 8 kilobytes. And so like, I've allocated exactly 3 sectors and now I'm freeing it and then I'm trying to allocate. Well, you might think you're going to try to allocate 4 sectors, but there's additional constraints where the allocation size actually has to be a multiple of P+1. So like if you're on, RaidZ 3, you're always allocating a multiple of 4 sectors anyways for a given logical block, right? So the more typical use case is like my blocks are big and I have like record size 1 meg, and yeah, like it goes down and now I'm actually allocating, it gets, well, if you have compression, then your block sizes are going to be kind of all over the place. And so you have little minor bits of fragmentation where it's like, some of my compressed block sizes are 300 kilobytes and some of them are 350 kilobytes. And some of them are 400 kilobytes. And now it's like, it's going to be kind of the same post expansion, but instead of being like 300, 350, and 400, they're going to be like 250, 300, and 350 kind of spread out over a slightly smaller range.
Aren't you leaving like individual sectors? For example, you're writing a lot, and now it can fit into less space. Because, for example, you have multiple stripe block,
Yeah,
and now we can fit into less sectors.
yeah,
So that will leave like some sectors.
yeah. So like, in theory, I see what you're getting at, where it's like I have a block that's 300 kilobytes, and then I touch it, and then I rewrite it, and now it's 250, and it leaves like 50 kilobytes of free space there. That's like not a very useful size. But the reality is we aren't rewriting in place. We're like freeing that old 300 kilobyte chunk and allocating a new 250 kilobyte chunk. And you can't like reuse it in the same TXG. You're probably going in and allocating it from the giant unused chunk of space at the end that we created as part of the expansion. So as long as you're doing that like a bunch, then you're going to be filling in the free space at the end. You're going to be freeing up a bunch of space in the middle. And yeah, you're freeing up a little bit more than what you're adding at the end, but it's still like a giant chunk of free space, because if you're like overwriting one big terabyte file, it's going to allocate like 1.2 terabytes at the end, and it freed 1.3 terabytes from the middle. And so there's really no significant fragmentation there. Yeah, George.
When you're in the middle of doing a reflow and you lose a disk and you pause the reflow operation, let's say the disk you lost was one of the original ones. I'm assuming that the new disk that you added, the space is still accessible and allocations continue to go to that. Is that true?
Yeah, the new disk, I mean, it's getting allocations, but the new space is not available yet. So, in the middle of the expansion, whether you've lost a disk or not, we're still doing, we're still doing reads and writes, and the new disk is involved in those for the space that's already been copied, right? So like we've copied some amount of the space and moved it to this new locations, which includes being on the new disk, right? So if your read happens to be from like one of the beginning offsets that's already been copied, it might be reading from the new disk. If the read is from like a later offset that hasn't been copied yet, then the new disk wouldn't be involved because we haven't moved it.
And
Yeah.
writing new allocations wouldn't actually go to the new disk?
Oh, so writes kind of work the same way, where it's like you do an allocation, we're still allocating using the old stripe width, and that could be allocated from the part that's already been copied or the part that has not yet been copied. So if it happens to be in the beginning of the disk that we've already copied, then yeah, like that space may involve the new disk, and so you're doing a write to the new disk while you're in the middle of the expansion. Yeah. Any other questions? All right. Well, thank you all very much.